Now I am taking 3 ml of phosphate buffer, this 1 ml, two ml and 3 ml of phosphate buffer. To this, what I will do is that I will add 5 microliter of HFA to it. Now this is the HFA, the same HF which I have been using. I will add this 5 microliter of HFA. Now what you can do is that you can in this stage may not use the cap out here, because we are not making any protein ligand interaction. This HF actually becomes soluble in water properly. Once you put it out here, mix it thoroughly, and then I am giving it for analysis. I am putting it in this chamber, doing auto zero. After auto zero, I am giving start. So this one is for only HFA and only HFA in phosphate buffer solution. So if we just lower the scale value to 0.1, here we can see there is a this absorbance for HFA. This will increase, so I am just increasing this one to 0.5. So it is almost a straight line, no such visible peaks out here in this region. So our curcumin is not present. Now this is the peak for HFA. So I am saving this one again as HFA. So let us change this name, not HFA, only HFA underscore 5. Okay. Saving it again as text file HFA underscore 5. So if we just for the time being completely remove these other spectra and enable this HFA, what we can see, it gives a peak of around, this one is around 279 nanometer. So if it keep it here 0 and this one we change it to 0.2, here we can see around 280 nanometer to 50 nanometer, it gives a lambda max value. Now what I will do is that I will again add HFA to it. So this one is for 5. Now I will again add another 5 microliter of HFA. So each and every time please make it sure to take a fresh tip and dip it into the HFA solution. Okay. Now I will take this out and I will mix it. Please note that bubbles are not formed out here. Sometimes bubbles are being formed, so we have to just remove the bubbles. Okay. Again we are transferring it. After auto zero, we will give it for measurement. Now in this region, in around 600 to around 500 region, there isn't any major changes in the UV spectra for HFA. However, here we can see the value, if we just increase this one to 0.2, here we can see again this value increases. Okay. So, initially what we were doing is that we are taking this curcumin and we are putting this cap, okay, the cuvette cap into it, and we are mixing it and then measuring the absorbance. What was actually happening out there? Curcumin sometimes precipitate in this aqueous medium. So, when we are adding HSA, all of the curcumin, rather the desired amount of curcumin is not coming into the aqueous solution in which HSA is actually dissolved. In order to do that, we have to just forcefully actually bring it into the solution by like mixing it like an up and down method. So, you can proceed with this method if you feel like, or in some advanced machines, UV machines, what happens is that there is a magnetic stirrer attached to it. So, you take a cuvette, that is much more reliable and much more accurate. What happens in the cuvette holder, as we can see in here, the cuvette holder, there is a magnetic stirrer. Okay, magnetic stirrer is basically common in the lab, but this one is quite a micro scale level. So, in the cuvette we actually put a small magnetic bit, generally known as rise bit, in such a way that it does not affect the cuvette or does not break the cuvette, and just turn on the switch on this magnetic stirrer. So, it will rotate, it will stir the continuously, and it will keep the system homogeneous throughout the reading. So, another error which I am just actually letting you know, this comes during the experiment. So, no need to worry, these are all manual errors which actually we face regularly. Another error is that while scanning from the 600 to 200, the scan speed I have kept as medium. You can keep it as slow also, and for slow scan speed the absorbance value is much more accurate, whereas for fast scan speed also the absorbance value sometimes accurate, sometimes may not be accurate, but out here we are keeping it at medium. Now, there might be some correlation with the change in the rate of this absorbance measurement, because what happens while this absorbance measurement is going on from 600 to 200 nanometer, within that time the solution is kept still. Okay. So, the curcumin within the solution, this unbound curcumin might settle down, okay, might settle down from there into the bottom of the cuvette. What happens in that case is that the entire solution may not be what is called available for absorbance measurement. Okay. So, that might lead to some error also out here. So, these are all manual errors which comes from time to time. So, it is always advisable to repeat this experiment 2 or 3 times whatever you are doing, so that to get an optimum value after the end of each experiment. Okay. So, now we are done with this up to HSA 5 microliter. So, I will save as only HSA 5, I will change it to HSA 10. HSA 10, and I will again take around another 5 microliter of HSA, take around 5 microliter of HSA. I am adding here, mix it thoroughly. In a similar process, we are going to do this auto zero. And after auto zero, we are keeping the start. Okay. So, here a blue line, it is not visible out here. Here there is a faint blue line, a sky blue line is coming, and again its absorbance is increasing. Here I guess it is now a bit not available right now, visible here. A small, there is a faint sky blue line. Okay. So, it is increasing. I am again changing this value to 0.5. So, again it increases as we have seen previously. These regions, what we can see, okay, I am showing you, just saving this one. This one I am saving as HSA 15. So, these regions, okay, this 2.0 or rather 3. So, these peaks, okay, we have also seen previously when HFA was added to curcumin, we can see the appearance of these sorts of peaks. So, these are actually the peptide bond, these absorbance due to peptide bond. Okay. 5. Now, this was for 15 and we will again add another 5 to make it 20. So, making auto 0. Then start. Well, this is one of the methods of analyzing this protein ligand binding using UV spectrum photometric method. There are various other methods which you have also seen, some you have also seen in the theory classes. Okay. However, apart from this one spectrophotometric method is also fluorescence. In case of fluorescence, what we do actually, we measure in a just the opposite way. We take the protein. Okay. So, just note it down, we are not doing out here, but just note it down. What we do is that we take a protein solution, we take the fluorescence emission of the protein. Okay. So, the protein meaning we are taking this HFA solution, human phenolphthalein, it has tryptophan residues and tyrosine also. So, we are not bothering about the tyrosine, okay, because as we know, if we take the fluorescence spectra of tyrosine, we will not see its actually emission lambda max, because due to the higher quantum value of this quantum yield of tryptophan, it will overshadow this tyrosine. So, what will happen, we are interested in the fluorescence emission of this tryptophan. Okay. So, what we will do is that we will take the fluorescence emission of tryptophan in HSA, pure HSA, and to it we will gradually add the ligand. So, out here what we have done, we have taken this ligand or curcumin and to it we have added HSA. Okay. In fluorescence, what we will do, we will take HSA and monitor its fluorescence spectra, that is fluorescence spectra of HSA, and to it we will gradually add curcumin. People might ask that why you are not taking with curcumin or all that. So, this is actually a standardized method. You can actually extend this method in whatever way you want, and you have to basically standardize it. Okay. So, this method works for all sorts of protein ligand complexes where in fluorescence spectrophotometer. So, out here what we can see is that again this absorbance value increases for protein. This 20. Now, I am taking 10 microliter. Okay. So, initially I have taken up to 20 microliter. So, I am taking another 10 microliter, the addition will give me total 30 microliter of HSA in the solution. Please note the amount of the volume, or rather the amount of protein or the amount of blank which we will take, it should correspond to that similar volume which we have taken in the previous case. Okay. So, suppose in the previous one we have taken like 20 microliter of protein, and now we are adding 22 microliter of protein, like 20 microliter of protein plus curcumin, and now we are taking only 22 microliter of protein. So, it will not work, because you have to take the exact volume of this solution in the blank only, which you have taken in the sample part. So, on a general note, we are let us just revise the UV curve of this protein, because you might be having your exams now, and so let us revive this one. So, the UV part of this protein, it contains 1 lambda max, that is around 278 nanometer or 280 nanometer. Okay. Now, for different amino acids, as we have previously seen, different amino acids are different UV absorption spectra, but we are bothered with the UV absorption spectra for aromatic amino acids only, okay, like phenylalanine, tyrosine, tryptophan. But most importantly, we are interested in determining the, or rather analyzing the UV spectra for tyrosine or tryptophan out here. So, this protein UV spectra do not have any remarkable absorbance or any remarkable sort of peak in the region above 300. Okay. So, scanning from 600, we do not have anything above 300, it gives in a region of less than 300, in a region of 280 or 278. So, this is a characteristic of protein, this is a protein spectra having a sort of amino acid residue which absorb, which have a chromophore to it. Okay. And apart from it, this region, as we have seen, make it to 4.0, this is for peptide absorption. Okay. Now, I am saving this one as HSA 20. So, what I have done, HSA 30. Okay. So, the previous one, actually I have to save the previous one also, but I am currently saving this one. Okay, I am showing you a small instrumental technique. Suppose you forgot to save any sort of data or any sort of spectra, okay, in the time well, but you will save it in a later part. Okay. So, how to do it? But for the time being, I am saving this one, this spectra 0.5, this deep violet color spectra, violet line. This one I will save as HSA 30, but I forgot to save the HSA 20. Okay. So, how to save HSA 20? Text file. Now, HSA 20 is actually this blue line. Okay. I am doing this one, HSA 20. I have not saved this one. Okay. Now, once you, there are 3 types of layer out here. Here you can see one is active, one is overlay, and one is stacked. So, currently we are in overlay. Okay. This one is stacked. These are different types of screen variation which we can see, and one is active. The active part is that which we can we are actually monitoring. The active part is the HSA 30. Okay. So, this is the active part. Now, if we click on this one, this green line, okay, this line is actually violet line. Okay. But if we just double click on this line, green line, double clicked on it, and if we come to active, we can see this has turned to green line. So, what is the basic fundamental part out here? If you have forgot to save any spectra while taking measurements, what you have to do it after experiment, you have to go to that spectra, double click on it, go to this active tab bar and see whether that color spectra is active or not, and then again you go here in the file, in a similar way save it as for 20. Okay, let us see if I have saved it or not. Okay, and save it as 20. Okay, okay, I am now saving it as text file, saving it as 20. Fine. Now, the last thing for the control is another 20 microliter. Now, I am taking 20 microliter. Initially, it was 30 microliter in total, and I am adding 20 microliter, which brings me the final volume to 50 microliter of HSA. Now, while calculating the concentration of HSA, please note to take the final volume in the way which we are adding this solution, like initially you are taking 3 ml solution, and to it you are gradually adding 5 microliter of HSA. So, the first concentration of HSA should be calculated in a volume, not 3 ml or 3000 microliter, it should be 3005 microliter, the final volume. Okay. So, in V1 S1 V2 S2, what you see, the final volume V2 should be 3005 microliter. Again, when you are adding 10 microliter of HSA to it, and the final volume is 3010 microliter. So, this total volume should be taken into consideration while calculating the final concentration of HSA in this cuvette. Okay. So, why we require the final concentration? Now, how to analyze this spectra, or how to analyze this interaction? Basically, if you get into the theoretical part, there is a equation called Bennesi-Hildebrandt plot. Okay. Basically, in easier terms, what we can say, we have to actually plot the absorbance versus concentration. Whose concentration? The concentration which you are varying. Absorbance will be on the y axis, not absorbance, I am coming to it, and concentration will be on the x axis. Coming to absorbance, the absorbance will be 1 by change in absorbance. Change in absorbance means 1 divided by, or rather the reciprocal of change in absorbance. The initial absorbance, like initial absorbance is the change from the absorbance of the ligand which we are measuring initially. Suppose in this case we have taken curcumin. Okay. We now will be measuring the change in the absorbance of curcumin, and we will be taking 1 by reciprocal to it, that is 1 by delta A. Delta A is a change in absorbance, and in the x axis we will be plotting concentration, that is the okay. In the x axis we will be taking 1 by concentration of HSA, because you are increasing the concentration of HSA. So, with increasing concentration of HSA, how the reciprocal of the change in absorbance is varying, you have to plot it, and from that plot, actually if you just do a bit calculation, from that you can get the affinity value or the binding affinity value. From that case, we can actually use to quantitatively estimate the value of the protein ligand binding. Now, suppose we are measuring the absorbance. So, at what wavelength or which wavelength we are interested in? As I said, it is 1 by delta A, but absorbance at which wavelength? So, the wavelength we are considering is the wavelength where the changes will occur, or rather in where the maximum change in curcumin will take place, which we can find once we get the subtracted values. Now, we will proceed for subtraction, that is we will subtract the blank one, that is the increasing concentration of HSA, that is the concentration of HSA from its respective curcumin plus HSA complex. Here we can see this interesting spectra with increasing concentration of HSA, we are getting an increasing value of the absorbance. Now, these are control. What we need to do is that we need to subtract. Subtract whom? So, let us first disable all this. Out here, from here what we have saved, we will be taking curcumin HSA, this is curcumin plus HSA, 5 microliter of HSA, and this is only 5 microliter of HSA. So, what we are doing is that, now let us enhance this one a bit, 0.3. So, this purple line or pink deep purple line is curcumin plus HSA, and this red line is HSA, and both the cases the HSA is 5 microliter. What we will do, we will actually subtract this one from this one. Okay. So, how to subtract? Here is a icon known as manipulate. Okay. Manipulate icon gives an option for subtraction. Okay. The type, here we will select data set, the data will take it from here, and the operation out here we will select as subtraction. So, this is a facility for this type of software, this instrument gives this facility. Other instrument might have some advanced facilities also. So, suppose what happens if your instrument does not provide this type of facility, what you can do is that, what conventional people does, we will take the text file, this text file for curcumin plus HSA 5 microliter, and we will take the text file for HSA 5 microliter and we will plot it in Excel and we will subtract it like the normal way. Out here we will take curcumin HSA 5 we have selected and we will subtract it from HSA 5 value. We just giving a random name sub 5 and this is the value for sub 5. Okay. So, I am just saving this one, I am saving this as FUB C5, which means subtracted curcumin for 5 micromolar of HSA. FUB C5, I am saving again this one as text file. Now, I am turning this off. Okay. This is SU subtracted file. Okay. The second thing we are going to subtract is curcumin HSA 10 minus HSA 10. Okay. So, SUB 10 again a random name. So, it gives another value. Okay. So, this value is actually a bit higher than this one. Okay. We are saving this one as SUB here C 10. Okay. And now what we will go, we will shift for 15, curcumin HSA 15 minus HSA 15, the calculators SUB 15. So, this one is for 15, we will save as again SU sub. In this way only similar we have to go on subtracting. Okay. Subtracting 15 and each and every time you subtract, please make sure to save these files. Next what I am doing is that I am doing 20. So, curcumin HSA 20 and HSA only 20. I am subtracting this one SUB 20 SUB C 20 and now I will taking this 30. Curcumin HSA 30 subtracting from HSA 30, calculating it. We are saving as again SUB C 30 and finally we have curcumin HSA 50 and we will subtracting from HSA 50. So, let us save this one again as not text file, this is curcumin C 50 sub C 50, save as this one. Okay. And now let us enable this one. So, what we can see out here, these peaks there is a bit distribution, some are increasing, some are decreasing. Okay. if we take it 0.5, so in this region 0.0. So, this region is quite not a very happy region, it is quite distributed in uneven process. So, we can change this one from 250, then visualize this one from 250, and then we can change this value again to 0.5. Okay. So, let us analyze this one. So, we are now disabling all those spectra, and this one is the spectra for curcumin 0.3. Okay, there is spectra for pure curcumin. Now, once we have added HSA, the actual value is actually not this one, okay, subtracted CH5. Okay. So, the next value is the subtracted value. Okay. So, this one is actually the intensity decreases. Now, again when you are adding 10 microliter of HSA, what is happening? You will be adding another decrease in value. In this way, what we can see is that this value again decreases. Here we can see a bit decrease in this value, okay, not this one, again this one, no, this one is actually the raw data, okay, this one, and finally this one. Okay. So, what we can see is that initially there is a bit decrease in, no, this one is actually have protein, this one have actually protein. So, yeah, this one. So, actually all those names have the similar name subtraction, so it will be a bit difficult to find out. For convenience photo I am showing that this line, this red line what you can see out here has a particular absorbance value. Now, some absorbance are getting decreased, some are increased. Okay, in this region some are getting decreased, some are getting increased, whereas in this region what you can see out here in around 300 region everything is getting decreased. Okay. So, for taking this delta absorbance value, delta A value, which region we are actually interested in? Fine. Which region we are interested in? We are interested in that region where the decrease or the change in the absorbance values are quite smooth. Okay. In all those cases, in all the cases, what we can say is that this particular region, okay, this one 400 nanometer region should be ideal, but as we all know, there might be some manual error while doing experiment, whereas in the next experiment if you proceed, what you can say is that it shows a gradual decrease. Here we have seen that from corresponding to curcumin spectra at 420 nanometer, when you have added HSA it gradually decreases, okay, up to 10 microliter, 15 microliter, but again it increases. So, there might be some anomalies might arise, okay. Where the anomaly lies, again I am telling this to you, an anomaly, there might be anomaly or there might be logic, okay. I am saying this to you a bit later. But however, for calculation you can go it in a region around 300 nanometer or this region which you feel is good enough for calculation. However, from here we can't actually quantify the extent of interaction until unless we plot the equations and get the Ka values. Okay. Now, what happens? Why you are getting this uneven distribution? Number one, there might be a manual error. Okay, that is a very easy solution or very easy problem to address. And number two, another thing might happen is that the curcumin, which you have first in the beginning, I am telling that curcumin might be actually not completely soluble in water. Okay, there is a problem with curcumin, it is not completely soluble in water. So, what happens when you are taking curcumin there, although you are mixing it, some of the fractions during the scan is getting precipitated. Okay. So, while it is getting precipitated, as you know from Lambert-Beer's law, the concentration or the light or the concentration of the solution is measured for those particular solvent only or solute only which is homogeneously mixed in water, okay, or in the solvent. Out here it is not homogeneously mixed. Okay. So, since this one is not homogeneously mixed and something is coming down in the solution, so what is happening? So, the absorbance value what we are getting is much lower. What we can say initial curcumin absorbance value what we have got without an HSA should have been a bit higher. If we had completely mixed it and dissolved it in water, or if we had taken a bit lower concentration of curcumin, okay, there are some actually errors which come time to time, and you need to actually do an experiment to find out where the errors are. You can't actually address the error in the beginning only. So, you need to do the entire experiment to find the errors are, and then you can repeat the next experiment only with the same condition. So, out here what is happening, the curcumin is actually settling down in the bottom. Okay. Now, when you are adding HSA, what is happening? Your HSA is combining with curcumin. So, it is well reported that HSA combines with curcumin. You can find in the paper HSA curcumin interaction paper, online it is available. HSA is actually combining with curcumin, it is forming an HSA curcumin complex. So, one interesting happens, what you know, when an insoluble component comes in contact with a soluble component, and the soluble component is of a much higher volume or much higher dimension than the insoluble component. So, what happens out there is that the insoluble components become soluble. So, I am explaining this in terms of protein ligand. Curcumin is very small, it is just a molecule, and whereas this HS is a vast molecule, it is a protein composed of hundreds and hundreds of small molecules, small amino acids. So, when the small curcumin attaches with the HSA, that curcumin might have been initially insoluble in the solution at that moment, but when it was coming in contact with this HSA, it is becoming soluble. So, its absorption increases, the absorption of curcumin increases. Now, again when we are adding more and more concentration of HSA to it, more and more curcumin are coming in contact with HSA, and more curcumin are getting solubilized in the solution. Initially there was no one to solubilize the curcumin, so it was getting precipitated. So, as we are increasing the concentration of HSA, so what is happening, more and more curcumin are coming in contact with HSA and its absorbance is increasing. On the other hand, something other might happen. Okay. So, when curcumin is getting attached with HSA, what is happening? Those curcumin which were initially soluble. So, I am explaining this for those curcumin which was initially soluble. So, when it is initially soluble, we have added HSA to it. So, what is happening? Those solubilized curcumin are giving contact with HSA, and when it is coming in contact with HSA, what is happening? Its exposure to solution is decreasing. Okay. So, this curcumin is no more exposed in the solution because it is coming in contact with our HSA. Okay. So, when it is in contact with HSA, it is no more exposed in the solution, rather it is exposed in the solution to a much lower extent, and as a result what is happening? Its absorbance value is decreasing a bit. And now, when you are adding more and more concentration of HSA to it, those curcumin which were not solubilized in water is becoming more and more solubilized, and as a result its absorbance again increases. So, the anomaly in absorbance which you might be getting in there for those components which are not properly soluble in water is maybe due to this reason, where the protein ligand interaction might result in solubility issues. Okay. So, in this way what we can say is that it is safe to take the absorbance in this region where there is a constant decrease. Okay. So, in this region there is a constant decrease in the absorbance value, and from there we can actually measure the change in the absorbance value. Now, we will see how the changes in the gallic acid occur in presence of HSA. We had seen how the changes in the curcumin spectra occurs in presence of HSA. Now, the next ligand which you are interested in is gallic acid. Here we will see a few changes in HSA spectra. Okay. For first, we have to take the UV absorbance of gallic acid. Now, in the similar way, we are taking 100 microliter of gallic acid. This is a cuvette. I have washed it properly, the same cuvette, okay, with double distilled water and then ethanol, and then I have taken 3 ml of phosphate buffer in a similar process. Now, I am pipetting out 100 microliter of my phosphate buffer, and again putting it 100 microliter of gallic acid, that is 5 millimolar gallic acid which I have prepared, mixing it thoroughly. And then doing auto zero. After that, start. So, gallic acid has a separate spectra should have a separate spectra. Now, this spectra is for curcumin. I have kept it for a reference. So, it is already 476, so no notable changes in this region. Gallic acid absorbs in a region, in a lower wavelength region. Okay. Here we can see that is its peak is emerging out here. So, this one is the peak for gallic acid. Okay. Now, this concentration is a bit higher, okay, because it is above 1. For that, what I will be doing is that I will be taking a slightly lower concentration of gallic acid in this case. Fine. So, you can actually proceed with this one, but it is better not to take the absorbance value above 1. But during experimental cases, if this type comes and you get a proper spectra, you can proceed with it. Okay. Okay, let me take the dilute solution, then I will just show you how the absorbance come and where are the peaks. So, out here we have taken a bit dilute solution of gallic acid. Fine. Now, for the timing, what we can see is that it does not show any notable peaks in the higher wavelength region, unlike curcumin. So, we may not take the higher wavelength scan at this moment. Okay. Why? Because it is very much necessary to not to waste this lamp intensity, because the lamp will be scanning from 600 to 200 and none of the peaks will be coming at this region. That is why we are actually shifting this peak from here, go to method, from 600 we will go into as 500, okay, just to actually retain the efficiency of this lamp and not to waste this lamp. Okay. So, we are again doing the start. Okay. We have to do auto 0. Fine. For that, let us do auto 0. And one thing is that if you change this wavelength range, sometimes some softwares might ask for again baseline correction within that range also. Okay. So, you might proceed with baseline correction first. Suppose you change from 600 to 200 region, from 600 to 200 to 500 to 200. Then again you can actually go for 500 200 baseline correction and again go for analysis. Now, auto 0 is done, we will go for start. Here you can see it has changed to 500. The scanning is taking place out here. Peaks are not observed since there is no absorption out in this region. Here absorption has started. Okay. Here we can see a new peak emerges. Okay, it is just below 1. And this peak is around, if you say 3.0, it is around 3.0. Okay, 3.5. So, here we can see generally two peaks of arises. Okay. So, this peak is below 250 region, around 210 211. Here 211 is shown, but the peak of interest we are interested in is actually this peak, which comes around 259 or 260. Actually, gallic acid absorbs around 260 nanometer. So, and another peak, not peak, a small hump which you can't actually see from here, but it is shown around this 250 or something like that. It is not properly visible, but out here this 260 region gives intense peak. And if we compare between curcumin and gallic acid, we can see that they have distinct absorbance peaks. So, as we have said that UV absorbance can be used to detect the type of compounds, it can this UV spectroscopy can actually discriminate the types of compound. It is very much chemically dependent, structure dependent. Okay. So, rather functional group dependent also. So, this is the UV spectra for gallic acid. So, I am saving this one as gallic acid only in this file and saving it also as text file, and for the timing and disabling this curcumin 1 and enabling this gallic acid. Now, what I will do, I will add to it HSA to it and see how it changes, but for the time being, since we have first seen how the HSA changes in case of curcumin, out here we are taking selectively a few volumes of HSA, a few concentration of HSA like 10, 20 and 50 or 30, and we will see how the spectra changes. Okay. Now, we will shift to HSA and add it when curcumin or rather gallic acid solution. So, we have taken this gallic acid to it and measured its spectra, and now we will add HSA to it. The HSA we will take here is 10 microliter of HSA. Here we are taking 10 microliter of HSA using a clean tip, micro tip. Here we have gallic acid and I will be adding here HSA, mixing it, and again I am taking this cap. Okay. Now, this cap has been cleaned. Okay. The cap which we will use for curcumin 1, it is better to use a different cap, or if you use the same cap, make sure to make it properly clean. Okay. So, now I am mixing it, transferring out here and doing auto 0. After the start. So, as we have seen, this one is also expected to come in a region near to it, because protenols absorb around 270 to 280. So, overlapping region might take place. Now, here I will be doing 10, 20, 30 or 50 as let us see how can we proceed. However, out here we have actually the control one, or rather the absorbance for HSA only, or like HSA only for 5 microliter, 10 microliter, those will be used for subtraction. Okay. Now, why I am using those? Because I am using this at a scratch. Now, if we use any experiment like here we are keeping the same temperature, same condition, same experimental part, at a scratch we are doing it. So, those control we can use for subtraction out here. Okay. Now, suppose what happens if we use this experiment, we do the curcumin experiment in one day and we do this gallic acid experiment in a second day. So, for each and every day make sure to take the control separately. Okay. But if you are doing it at a stretch, you can carry out, but it is always better to if you do it separately. So, this one as we can see 0.2, this one again it increases this value, we can label this one as gallic acid HSA 10 and save this one as also in text file. Now, what I will do, I will again add 10 microliter in order to make the final volume of HSA in it as 20 microliter. Now, I will be adding again 10 microliter to it, taking this cap, mixing it thoroughly, okay. And after mixing doing auto 0. Please make sure that the solution does not spills out when we are mixing it. Now, for convenient, what you can do is that you can use a bigger like micro pipette, like you can use this type of micro pipette, okay, which have a greater tip, micro tip. This one is a bigger micro tip. you can actually put this one within the cuvette chamber, or rather the cuvette, and you can actually mix it. You can actually do this one up and down. If you do this up and down, it will just take solution from here and it will just mix it. If you are not comfortable using that up and down method using hand, you can do it using a micro pipette. So, let us see how this observation comes. So, again here we can see it is increasing. So, what happens basically, there is a overlap region. So, as we are increasing the concentration of HSA, so its absorbance also increases. Now, we are saving this one as gallic acid HSA 20, gallic acid HSA 20. Okay. After that, to it I will be adding another 10 microliter, so it will be 30. So, generally some confusion arises, how many readings should one take. Okay. It is always better to take minimum 8 to 10 readings. Out here, due to tutorial class, since we are bothered with the nature of the curve, so we are not going into details into the number of readings. Out here I am taking 5 to 6 readings for curcumin, a bit lesser in this case. Okay. But while you are doing an experiment, make sure to take minimum 8 to 10 readings. Why? Because when you will be plotting out there, so what happens, you might see that some readings might have errors. Okay. So, out there minimum from 8 to 10 readings, you can see 3-4 readings might have error. Okay, that the change is not in a regular fashion in which it should have been expected. Okay. So, in that case we have to just omit those readings. Okay. But if you have only 5 readings, okay, and you omit 3 of them from that only, so you are left with only 2 points and you can't actually draw any straight line or acceptable straight line. Okay, you can draw straight line within 2 points, but not for any experiment. For an experiment you need minimum 5 to 6 points. So, if you take at least 8 to 10 points, from there easily you can deduce, you can subtract, or you can leave 3-4 points which are having error, and then you can plot it using 5 to 6 points. So, here again the absorbance is increasing. So, 1.5 absorbance has increased, and this is gallic acid and HSA 30 micromolar. Now, we will going finally into 50 micromolar, that is the final concentration. So, we will set it at around 20 microliter, and we will add 20 microliter of HSA to it. We are setting this micropipette to 20 microliter. Okay, as this is I am also saying this is a division class. So, in this way what you can see is that this is a micropipette, this is a 20 microliter micropipette, 20 microliter, and here the readings are there. These you have already studied in the first class. So, just a reminder, this is a 20 microliter pipette, and here you can see the graduation, this 200 indicate that it is actually 20 microliter. Now, I will be taking 20 microliter of HSA from it. Now, I will be taking 20 microliter of HSA, and please remember to use the same HSA solution for sample and control. Okay. Do not change the HSA solution or the concentration. This is for 50. Auto 0, and now starting this one. Here we can see the value gradually increases. Okay. So, this part is actually enveloped. Here we can see a small hump. This one, this red line and blue line, green line, here you can see a small hump is arising here, a small hump followed by another peak. So, this hump is basically due to your absorbance of HSA out here, because HSA gives, this hump comes around 280. So, HSA gives around 270 280 for HSA. So, I am saving this file again as GA HSA 50 and HSA 50 text file. Now, we will do the subtraction and see in which range the values come and how the changes occur out here. So, again for the subtraction we will go to this manipulate option, we will select data set, already subtraction operation is activated. From there we will select GA HSA 10 and will subtract from our HSA 10, which is somewhere out there. It's a 20, okay. So, we have to search it properly. So, HSA 10, calculating it, S10, okay. So, it is coming. I am going into details about the changes spectra after a few minutes. I am saving it as SUB GA 10. Okay. So, for 10 micromolar of HF, this is a change, and again I am saving it in text file. And the next thing I will be doing is I am taking GA HSA 20 and I am subtracting this one from HSA 20. Okay. So, just subtract. So, what I am getting is 20. Okay. Save as SUB GA 20. Text file. Okay. So, now what I am observing out here is that if we just highlight this and zoom this point. So, let us suppose 1.0 and the lower part let us enhance to around 0.6. Okay. So, it is not clear to that extent. Let us change this one as to 30 and this one as 300. Okay. So, interestingly what you can see is that, or let us say this one as 280 and this one as 240. So, this is the region where the change is occurring around 260. So, here we can see there is not a major change in the intensity, but this one where it is gone. So, gallic acid only. So, this is the green line where you can see the gallic acid only, the green line. Okay. The green line appearing and disappearing, this is for only gallic acid without HSA. Now, when I am giving this 10 microliter of HSA and 20 microliter of HSA, so you can see here 10 microliter, 20 microliter HSA. So, it is decreasing in the first two cases. Now, let us see what happens when you subtract for higher concentrations. HSA 30, HSA 30, calculate F 30. Now, again here we can see this F 30 decreases. Okay. Save as CUB GA 30 and the final one out here is 50. So, we have to search from here. So, how the files come? Files basically comes out here in the way that you have arranged their names, and according to the names this comes. Okay, so you will be searching for GA. Okay, it just went up here. GA HSA 50, and from there HSA only 50. Where it is? HSA 50 F 50. Well, it again increased a bit. Okay. Save as, yes. If we change a bit like 0.7, 0.92. Okay. So, this one here we can see we have completed the subtraction, and this one is for only gallic acid. It has gone here, only gallic acid. Okay. Out here the absorbance in addition of HSA, when you have subtracted the control, that is only HSA, decreases. However, here we can see 1 or 2 points, the decrease is not in a regular trend, like 3 are decreasing and again 2 are increasing again, but the absorbance value is lower than gallic acid. Okay. So, what is happening out here? So, gallic acid is actually soluble in water, we all know. Okay, solubility has some issues, but it is in a soluble in a better extent than curcumin. So, when it is soluble in water, more or less most of the gallic acid is actually distributed homogeneously in water, and it is showing absorbance. Now, it is binding with this protein HSA. What is happening? Gallic acid is not at all exposed. Now, why this absorbance is decreasing is a very primary question. What happens is that absorbance, why absorbance is shown? Because when a molecule is exposed to the light, okay, incident light, it absorbs this incident light. Suppose a molecule is actually bound by this light. Okay. Suppose this is, okay, if I give you an example, if I give you a some sort of small example out here, what you can see is that suppose this is a molecule. Okay, suppose this is a molecule, this is actually a lead of the falcon, it is a cap of the falcon, the molecule which shows a UV absorption. Okay, so the absorption is shown in the region around 260 as in gallic acid. This is for just for gallic acid in this region. Now, it is absorbed, it is light is emitting, entire part of this gallic acid is exposed in this room, as we can see. Suppose this room is actually the UV chamber or the cuvette. Okay. Here this is the gallic acid molecule, it is exposed to the light, okay, this molecule. Now, suppose my hand, okay, my hand is actually the protein, okay, this is HSA protein. Suppose my hand is actually the HSA protein which is coming, and this is the molecule. Okay. Now, once it is coming here and it is attaching this in this way, here you can only see my hand. Okay. So, the incident light is actually only seeing my hand, or incident light is only seeing the protein molecule. It is no longer seeing the gallic acid, it is seeing the gallic acid, but at a much lower extent. In the cuvette, what is happening? The gallic acid is actually facing the light. Okay. So, suppose this one, this is the cap of the falcon, I am taking this as a example. Suppose this room, this entire room is a cuvette. Okay. And this is actually a cuvette in which this is a molecule of gallic acid. It is hovering here, here, here throughout, okay, doing Brownian motion, all those things, fine. So, now what is happening out here? This gallic acid is absorbing light. So, the light actually, suppose any light which is incident on it, this is the UV light. Okay. So, the UV light is absorbed by this gallic acid. It was free initially, it was happy. Now, when we are adding HSA, protein molecules are coming. Suppose my hand is actually this hand is actually the protein molecule. Now, when protein molecule is coming, this suppose this gallic acid, this was absorbing from this side, it was absorbing from this side, here, there, throughout the molecule, throughout the surface it was absorbing. Okay. So, now what is happening is that when this protein molecule is coming, it is attaching to this part. Okay. This gallic acid is getting attached to this protein molecule. Now, when this gallic acid is getting attached to this protein molecule, one part of this gallic acid is facing the UV light or something like that, or rather the UV light is not at all being exposed to this gallic acid. So, here what we can see that more or less you can see my hand only and you can't actually see the gallic acid anymore, or rather you can see a small fragment, a small portion of this gallic acid. So, what is happening when the protein is getting bound with this ligand, only a small part of this ligand is exposed. So, the entire ligand cannot actually absorb from there. Okay. So, what is happening, it is actually the extent of absorbance or the amount of absorbing power of this ligand actually decreases, because it is not attached, it is not at all exposed to the UV light, and as a result its absorbance value decreases. Now, what is happening in the actual case is that suppose this due to this one there is a lots of rings are attached, lots of functional moieties are attached which are responsible for absorbance. Suppose one ring is getting attached to the protein molecule which is responsible for absorbance, and that absorbance corresponding to that ring is decreasing. Okay. Several things might happen in the medium, but out here due to this protein ligand interaction, and this is the reason in which this molecule the absorbance is decreasing. Whereas in case of curcumin, what is happening in curcumin, like this is hovering here and there, curcumin was settled down like this way. Okay. So, curcumin was down, it was not there, it was not hovering in this region, but when protein came it rescued curcumin. Curcumin is a long molecule, one part of the curcumin is actually becoming into solution, whereas other part is not. So, due to change in the functional moiety, actually curcumin and gallic acid are different functional moieties, functional compounds. Okay, different functional moiety, change in absorbance might differ. From this way we can actually estimate what is the extent of interaction, what is the extent of interaction between the ligand and the complex and the protein. Now, this is the change in the structure, change in the absorbance of our gallic acid in presence of HSA. Now, from here we can actually take the delta A in the region around 260, because it do not have any other absorbance region, and here we can see this region is quite what we can say, it decreasing in a very systematic way or in a regular way, and here we can take this one with increasing concentration of HSA and we can plot this one. Okay. And from this plot we can take actually the ratio of the slope or ratio of the, actually we have to take the ratio of the intercept and slope. Okay. So, intercept by slope, if we just take it, we can get the Ka value, and if we compare the Ka value between the curcumin and the gallic acid, we can know which one interacts with protein, and we can actually quantify the extent of interaction. So, we have seen how to carry out the experiments concerning protein ligand interaction. Initially we have taken HSA solution 1 millimolar HSA, and we have prepared gallic acid as well as curcumin. Okay. We have taken gallic acid, we have dissolved it in double distilled water, and we have taken curcumin, initially dissolved it in ethanol. Okay. This ethanol is actually HPLC grade, high grade ethanol, and then from that ethanol we have taken a small amount of ethanol in double distilled water and made up the volume, and the water in the water and ethanol mixture, the percentage of ethanol is better to keep it around 10 to 20, or around 10 is better, 10% ethanol is good. Do not increase the concentration of ethanol, then it will harm your protein. Now, after we have prepared it, we have shifted to this UV instrument, where we have initially taken a cuvette, done the baseline correction with phosphate buffer pH 7.4, and your concentration is around 20 millimolar. And now to it we have gradually added HSA, but before that we have taken curcumin to it. We have actually studied the UV absorbance of curcumin. We have seen how the peaks of absorbance spectra curcumin comes, and we have added HSA to it, and it gives particular spectra. And we have taken another blank which contains only phosphate buffer and HSA. We have subtracted that absorbance of HSA from curcumin plus HSA solution, and we have obtained only HSA solution, okay, only curcumin solution, fine. And after that we have plotted it, and again we have taken this gallic acid, taken its absorbance, added HSA to it, taken absorbance for gallic acid HSA solution. After that we have taken only HSA and subtracted it. So, in a nutshell what we have seen, we have taken the ligand, taken its UV, added the protein, and finally got the spectra and subtracted it from the control, which is only the protein. In this way we actually can estimate the protein ligand interaction and observe it. Now, there are some other ways in which we can do it, monitor it using this UV tool only. Suppose we want to monitor with change in temperature how the interaction varies. So, what we can do, we can actually increase the temperature, and actually we can, for that part what we need to do, we need to take a ligand and we need a protein at different temperature. We can study the protein ligand interaction. We can study the protein ligand interaction different pH. We had taken phosphate buffer pH 7.4, we can do it at phosphate buffer pH 6 also. So, in different way we can actually regulate the protein ligand interaction. Why at different region? Because in our body the pH varies, at some region temperature varies, some region the environment varies. So, in order to mimic a biological system or a biological process, we have to change the medium. This is the most generalized medium in which we are using actually a phosphate buffer. If we change the different temperature and other pH conditions, in this way what we can do, we can actually get a outlook of how a protein ligand interaction might take place in a biological system. So, I hope this experiment was helpful in giving you an idea how a ligand or how solutes might interact with protein and how the absorbance of the solutes might change in presence of protein. So, thank you.